the derivative of the inside with respect to AI, which is 1. Everybody agrees? So this is partial L over partial AI. Okay, let's go to the next part. What will be partial L over, partial AI, the second part here. Partial S. Okay, what is the expression for S? AI in terms of S? 1 over 1 plus e to the minus s, right? So let me sidetrack for a second and show you what is the derivative of the sigmoid. Okay, so remember sigmoid is fx equal to 1 plus e to the minus x. So what will be f prime x, meaning the derivative with respect to x? Okay, there's a couple of ways we can do it. We can treat it as u over v, right? Which, if you remember, is v u prime minus u v prime over v squared. So let's do v will be 1 plus e to the minus x times u prime will be 0, right? Minus u 1. Derivative of this with respect to x, what will that be? Wouldn't that be minus e to the minus x? Right? Okay, divided by 1 plus e to the minus x squared. Right? So what will this be? Minus e to the minus x over 1 plus e to the minus ex squared.
Plus minus.
Oh, minus minus 1 plus, correct. Okay. So now suppose I call this some output A. So A equal to fx. So A is defined as, or even if I leave it as fx, what you will see is this will turn out to be fx 1 minus fx. Okay, well, let's verify it. Okay, just focus on the right part. What is fx? 1 over 1 to the, what is 1 minus fx? 1 minus 1 over 1 plus e to the minus x. Right? So this will become 1 over 1 plus e to the minus x. Everybody agrees? Right? 1 will cancel as and ex will be left at the top. And isn't this the same as this part over here? Okay, so anytime you have to take the derivative of the sigmoid from now on, whatever the output is, if you multiply it by 1 minus the output, that will be the derivative. So coming back over here, what I'm trying to say over here is AI over S, we needed to go partial AI over S. Essentially, if this is sigmoid, what will this be? AI. 1 minus AI. Okay, third term that we need over here will be what? Partial S over partial W1. Okay, so now go to over here. Take the derivative with respect to W1. So what will that come out to be? XY. Okay, so now we can plug all of these things over here. So this will turn out to be 2AI minus pi I times AI 1 minus AI times x1 is the partial L over partial W1. Okay, if some training data is given to us, Okay, somebody gave us the weight, height as 65 inches, weight as this, right? And told us the expected output in this case is a 1, meaning somebody has diabetes. So my question is, in this part over here, can we compute this? Okay, what will be x1 in this example?
The first feature.
The 65, right?
Yes.
So we know this number. Do we know what is the actual output?
Actually, if you compare,
In the beginning, all these weights will be randomly initialized, so these are just numbers.
yes.
So sure, we can add them up, we can pass them through the sigmoid, and let's say this produces 0.81. So what will be AI then? 0.81 times 1 minus 0.81, right? And yi, what will be yi in this example? 1, right? Because we assumed we already know it for this data. So then, do we know the exact number for partial L over partial W1? Okay, now can we go, and in the beginning this was randomly initialized, suppose this was 0.31. Alpha is typically fixed. Alpha, if you recall, is called the learning rate. For example, could be 0.1. Partial L over partial W, you know, we know each part, we can find that out. So can we find the new value for the W1? Right? Same thing we can do for W2 and so on. And if we keep repeating it over and over again for all the data, ultimately we'll stabilize whatever the final W's and B's are. Those are our answer. Yes?
How do we choose the alpha?
How do we do what?
How do we choose like the alpha?
Alpha typically is small, like 0.1 or 0.01. How do we choose it? Once I go to my laptop, I'll show you something neat.
Is there an intuitive explanation for why the gradient descent gives us the optimal weights?
It does not give us the optimal weights. It tries to give us close to optimal. And the answer comes from the theory of nonlinear systems. Like I said, even for example, in logistic regression, to find the parameters, we were using gradient descent. Anytime we have a nonlinear equation and we needed to minimize some loss, find the parameters, gradient descent is a popular numerical technique. Okay, so is everybody clear with how a single neuron system will work? Okay, so my question to you is, how is it different from logistic regression then? Do you see any difference in what we did here? Yes.
I mean, activation function can be different.
Let's pretend activation is sigmoid. Then is there a difference?
The only difference is when we pick the partial with respect to the weights, we have that extra term of 2 times AI minus YI. Because the gradient, when we do in logistic regression, the gradient was defined as AI 1 minus AI times x1. So that's part is the same, but we have this extra term now.
Yes, almost
Yes.
the right answer. Focus on the loss function.
Different.
What was the loss function in logistic regression?
Most likelihood.
It was log likelihood, right? Whereas here it's a simple error square. Okay, so that's one difference. As a result, so in your next assignment you'll be comparing the same data that you use for logistic regression. You'll do it this way with a single neuron and see which one does a better classification. I'll give you the data, right? Okay, so anyway, single neuron system is extremely easy. So let's make it more complicated now.
Professor,
Yes.
before we continue, we in our last gradient we have a dependence on I, so AI, so that's an iterator. So
AI basically means, see, all of these, if we have 10,000 training data, right?
yes,
We pick the first data. So think of I as
the iterator, yes.
on the training data, not on the features. So this is the data for the first person. So AI is the output as a result of the data for person I.
So, but then when we compute the gradient, shouldn't we find that same for all AIs? For all i's in the range of I is equal to 1 all the way to n?
But W1 is independent of the I. Okay, see the data changes as we feed in
Yes.
data for a different person, weights do not change.
So it will adjust with each person.
Okay,
You
so
don't
we.
have to do that at the same time.
Yeah.
Alright.
In the end, doesn't matter what person it is, once these have stabilized, they'll be used for all persons. So they don't have the I in the weights. Okay, so now let's create a 2-neuron network. So let's pick an example. Okay, 2 layers. Or maybe with 2 neurons in hidden layer. Okay. And to make it extremely easy, we'll pick 2 features only. Okay. So our architecture is like this. We have 2 features, x1, x2. Okay. We have 2 neurons. Every neuron has some and then some in the activation function. Okay, so let me call this W1, W2, W3, W4, W5, W6. Okay, let me call this A1, A2, S1, S2. Let me call this S3, and let me call this A3. Right? Then we will pass it through the loss function. And this would be L, this would be Y of I, as an example. And let me just put Y. We'll assume I is implied for whatever data we are feeding. Okay, so again, this is a binary classification system. As you can see, if the output is produced close to 1, then it belongs to one class. If the output is produced close to 0, it belongs to another class, right? And if the activation is sigmoid everywhere, then we will guarantee the output will range between 0 and 1, right? Okay, all right, so our goal is to develop the equations so that we can train this network. So develop, oh, I forgot the biases, thank you. So let's call it B1, let's call it B2, and let's call this B3, right? So our goal is to develop the gradient descent equations for determining weights and biases during training. that's our goal, right? Okay, so let's set up these equations. So in other words, as you can see over here, what do we have to find out? We have to find out partial L over partial W1, partial L over partial W2, partial L over partial W6, right? And partial L over partial B1, partial L over partial B2, and partial L over partial B3. So if we can compute those, then given some training data, we can iterate through these and easily find out what is the model parameters, meaning W1 through W6 and B1, B2, B3, right? Okay, so let me see if you guys can help me develop these equations. So let's start with partial L over partial W1. Okay, so our goal is to find from here to here, right? So what will be, see again, easy way to do it is, like I said, trace the path. So how can we go from the loss backwards to W1?
So partial L over partial A3.
Partial L over partial A3, very good.
Then partial A3 over partial S3.
S3,
Then partial S3 over partial A1. And then partial A1 over partial S1. Partial S1 over partial W1. Yes.
W1. So you can see the chain of partials getting bigger and bigger, right?
And we need just one way, right? Because we
No,
also
these
can
are,
go-
there are 6 different ways. This is just for W1.
So
Yeah, so total in our model, we have 9 parameters that we need to optimize through gradient descent.
it's under this layer and 3 in the other layer.
Yeah, so let's now take a look at the equations for this. What is the equation for the loss? If we are using,
Not negative?
so y minus, it doesn't matter which way we write, y minus a3 squared is our loss, right? Okay, so what will be partial L over partial a3?
So it's minus 2
Won't it be minus 2
y
y minus a3?
Yes.
Okay, what about a3 over s3? If this is sigmoid,
A3 is
So 8 being 1 minus 8.
right? Because that's the derivative of the sigmoid. Whatever the output is multiplied by 1 minus.
Yeah.
What about S3 over A1?
3, so this is the
See,
so it's
Before you
W5.
answer S3 over A1, write the expression for S3. What will be the expression for S3?
W5 times A1,
A1 times W5 plus
A2, W6,
A2 times W6 plus B3.
3, yeah.
So what will be partial S3 with respect to
Weight 5.
weight 5? So this is basically this part, correct?
Yeah.
What about A1 over S1?
Is sigma again?
It's sigmoid.
So A1 times 1 minus A1.
Okay, and lastly, S1 over W1. So what is the expression for S1? S1 is X1 W1 plus X2 W2
divided by X squared.
plus B1.
So it should be
So partial S1 with respect to W1,
X1.
X1. So do we know partial L over partial W1? All of these will be numbers. We can compute them, right?
Yes.
Okay, very similarly, can we find partial L over partial W2?
Yes.
What would be the difference between this and this?
The weight
X2
5 is
and
weight 6. The weight 5 is the same and then X2.
Everything else stays the same. Take a look, the path is the same, except we're going this way, right? So in the end, we are doing partial S1 over partial W2, which will be
X2.
X2. So this will be exactly the same. It will be X2, right?
Yeah.
Very similarly, let's do one quick partial L over partial W3.
First to
Yeah,
understand.
first one.
So first, let's write the whole thing. Partial L over partial A3, partial A3 over partial S3. So we come up to this part, right?
Yep.
Then we have to go to W3. W3, as you can see, is coming. So the path that we need to follow for W3 will be something like this. Everybody agrees?
Yes.
So up to here is A3 over S3. Then what should I do?
Yes.
Over the
Or
W.
A2.
Partial S3 over
Partial A2.
A2. Then partial A2 over
S.
A2 over S2, correct?
Yeah.
Then partial S2 over
Partial W3.
partial W3. Okay, very quickly let me put the numbers. L over 3 is minus 2 y minus A3. S3 over, what did I have over there?
You just did the first one. You now on the second.
Oh, A3 over partial S3, which will be A3, 1 minus A3, right? Then, what did I say over here? S3 over A2, right?
Which is W6.
Okay, if you take a look at the expression for S3, did I write it somewhere?
No, we have.
Not yet.
So let's write it S3 equal to W5 A1 plus K2 W6 plus B, right? So we need S3 over A2. So that will be W6. Then this will be A2, 1 minus A2. And then S2 over W3. What's the expression for S2? X1 W1 plus, sorry, X1 W3 plus X2 W4 plus B2. So if by the very last part I need is S2 over W3, so what will this be? Right? Anyway, you guys get the idea. So same way, you can find any of these, right? What if we wanted partial L over partial B2?
The same thing, but one at the end, so we don't.
Yeah, because if you take a look at the end, it will be partial S2 over partial B2, which is simply 1. So it will be exactly the same thing, except at the end it will be just 1. Everybody agrees? Okay. Very quickly, one more thing before we move to a more complicated network is what about, let's go partial L over partial W6. So let's try to find partial L over partial W6. So again, what you do is like take a look at the path to go to that, right? So we'll start from here, and then we'll go, this is where we'll get to W6, right? Okay, so won't it be in this path, partial L over partial A3 times partial A3 over S3 times partial S3 over W6. So you stop at W6. You don't go to the previous output because this is what we are interested in, right? So now this is easy. Partial L over partial A3 is minus 2y minus A3. Partial A3 over S3 is a sigmoid. So A3, 1 minus A3. And lastly, what will be S3 over W6?
A2.
It will be the previous output, which is A2. Okay, so in general, if we were to given some data, and we were to come up with what should be the weights, what should be the biases, we start out by randomly initializing all of these. Then we compute the gradients, partial L over partial W1, W2, and so on. And we keep adjusting W1 equal to W1 minus alpha partial L over partial W1, W2 equal to W2 minus alpha partial L over partial W2. Same thing go to 6, B1, B2, B3, alpha partial L over partial B1. So basically we will keep repeating this over the training data given to us over and over again until they stabilize. What we do is, as we update the weights, every time we'll compute the loss again. Okay, and if we plot the loss, so suppose we are looping through 100 times, right? Suppose those are the iterations. In the beginning, you can see loss will be high. So if loss is being plotted on the y-axis, gradually you'll see it will go like this. It will not improve, so there's no need to train it more. Okay. This is the ideal case. In reality, the loss may go something like this. Anyway, gradually we'll take a look at how do we make this loss go as fast as possible, go down. Okay, so everybody can easily see how we develop the equations for 2 neurons in the hidden layer, 1 neuron in the output layer. So this was pretty easy. Now let's make it more complicated. Let's put 2 neurons in the hidden layer, 2 neurons in the output layer, and see how will our gradients work out. Okay, and by the way, see all of these equations. Okay, gradually, like I'll, have you feel more and more comfortable with the mathematical terminology. So we often talk about the model. So the model in this case are the weights and the biases. Okay, so after trained, whatever weights we fixed, we determined whatever biases we found out, those are referred to the model, right? In the general terminology, the model is referred to as theta. So if somebody says, what is the theta for this particular neural network, essentially it means what are the values of the weights, values of the biases that we have determined through training, right? So then if you take a look over here, we can easily write this in more compact form. We can say W of I. So I is not the training data. I, in this case, is 1 through 6, basically. Okay. W of I minus gradient of W of I of alpha times the gradient of I of the theta. Or, sorry, I should write it partial with respect to theta of the loss function. Okay. So anyway, all that means is we determine the loss with respect to theta. So actually, the better one would be theta equal to theta minus. Okay. So this is what we are doing. Theta could be one of the weights as an example, one of these biases. So we are basically adjusting according to the gradient. And this is inverted triangle is another way to indicate the derivative, right? Okay, so very quickly, let's go through. Okay, our goal is to be able to understand how do we train deep neural networks with hundreds of neurons in each layer, many, many layers, right? So I'm gradually building up that background. So let's now create 2 neurons in the hidden layer. So there's one. Here's another neuron. Okay, so the output goes over here, output also goes over here, output goes over here. Because there are 2 outputs, there will be 2 expected outputs, y1 and y2. Okay, and suppose we have 2 inputs. Okay, and everybody will have a bias. Bias here, bias over here. Okay, so that we can come up with a better terminology, so that we can handle the training of any number of neurons over here, any number of neurons over here, any number of, right now we have 2 layers over here, any number of layers, so that we can generalize it easily, right? What we will do is, we will pick a special notation for describing the weights and biases in each layer. Okay, so our notation for the weight will be, okay, Wij and some k over here. So the top will be the layer number. I will be the output number. J will be the input number. Okay, so for example, if I go over here, W, okay, because this weight is for the very first layer, at the top I'll put 1, right? Okay, now think of this way as the first output and the second output, right? We always write which output this is going to, the first, right? And which input it is? First. Okay, so let me see if you can figure it out. What will be the W over here for this one?
One at the top.
One at the top.
2, 1.
1 at the top.
Yeah.
Agreed.
2, 1.
It will be 2, 1. Okay, let's go over here. It will be W,
1, 2.
1, 2. And lastly, W, 2, 2, 1. Right? Okay, bias